Okay, good afternoon everyone, and thanks a lot for joining us today for the launch of our seminars Future Forward, Science in the Open Era. And today, all the seminars are organized by TU Delft Library, and our today's speaker is Tim Smith, so thank you very much for joining us and agreeing to do the keynote opening talk. But before I start, I just wanted to make some organizational announcements. So just to tell you that today's talk, together with the questions from the audience at the end, will be recorded. So we have Jos in there, and also we have a photographer, Jan, our chief photography officer down there. So can I just ask, we are planning to make all this photography and the videos publicly available after the talk. So can I just ask people, can you nod your head if you're okay with being recorded? Thank you so much. I can see everybody nodding. In case anyone objects to being captured on videos, on photographs, please approach Jos or Jan down there and tell them that you don't want to be captured. Thank you very much. So that's a great pleasure to welcome Tim Smith today, who will do the inaugurational talk of our seminar series. And just to tell you a little bit about background of Tim, so he did his PhD in particle physics and performed research at the Large Electron-Positron Accelerator for 10 years. And he is now the head of collaboration devices and applications group at CERN. And just to mention a couple of his achievements at CERN. So first of all, he drove the launch of CERN's open data portal to share Large Hadron Collider data with the world. And very interestingly, he also was involved in launching the Higgs boson webcast, which perhaps some of you have seen, which shared its exciting discovery with the whole world live. So quite exciting stuff. And he's also overseeing there's another repository, which some of you may know, and some of you I know have been using it, and that's a data archive which anybody in the world can access to deposit data or to use data which is available in there. And in general, our team is leading open science activities within his domain and also like in science globally, internationally, in the whole world. So thank you for joining us today. And personally, just to tell you, I know Tim for a couple of years now, and the first time we met at the Research Data Alliance meeting where Tim gave a very inspirational keynote speech about how important data, good data management and sharing is for reproducible research. And since then, Tim helped me and my colleagues in my previous job at the University of Cambridge on several occasions and sort of became our informal mentor on our open science activities. So it's really nice to have Tim coming to us at TU Delft. And just to mention, put these talks in a more context and, why do we have this title today? I think at TU Delft, in addition to the usual problems like, should we share data? At what stage, in what format, what data should be shared. We also have lots of issues resulting from numerous industry collaborations that we have at TU Delft. That's one of the important elements, important aspects of us as a technical university where we develop new technologies, where we develop some new commercial interesting findings. But of course there are some tensions between the needs of open science and the needs for commercial protections of our intellectual property. So Tim has a lot of experience of dealing with all those questions. So without any further ado, I would like to welcome Tim today. We are very excited to hear your talk, and please join me in welcoming him very warmly.
Thank you very much. Thanks. So thank you very much for the very nice introduction, and thank you very much for inviting me here to talk about open science. So as Marta said, I deliberately chose to highlight one particular aspect, perhaps the commercialization, the risks and the opportunities that might bring. But essentially this is an open science talk. So in choosing to call it Research Market or Research Commons, I'm conscious of the fact that in a market there are two things, goods and services. And so throughout the talk I'll try and emphasize the goods and services in research. So jumping straight into the goods. So who of you was motivated by going into research for fame or fortune? No? Who wanted to be on the front page of Marie Claire or the front page of GQ magazine? No? Not many of you. That's because these vanity presses, the goods, are actually the personalities, the people. And for us, that's not what motivates us. At least it wasn't for me. I came in because of the curiosity, the want to understand, the quest for knowledge. And knowledge is the real goods of our business. In fact, knowledge was the driver for us to launch the World Wide Web. The initial slogan of the World Wide Web was, let's share what we know. And when we built it at CERN, Sir Tim Berners-Lee built it, it was actually about 30 years ago. We're just about to celebrate it in 2 weeks' time, the 30th anniversary. But when we built it, we connected the knowledge centers in particle physics of the time together so that we could share more rapidly all the information amongst ourselves. So the centers, CERN itself and the centers around Europe, NICEF, of course, just around the corner. The first ever web server across in the States, you may not know, was the Stanford Linear Accelerator preprint server. So the States got off in the right direction with sharing knowledge to start with, which was great. So if we fast forward 30 years later, the web has absolutely transformed our world. And now there are 2 billion websites. This is a schematic of the interconnections between those websites. And you can find no end of information anywhere on the web. But the information might be right and it might be wrong. It might be made up. And you can't tell the difference anymore. So ironically, the growth of the web has made it actually more difficult to get to those knowledge centers, which is an awful shame. And now we've replaced some of our filtering mechanisms, unfortunately, with the seeking after likes or retweets or subscriptions, and basically replaced truth with popularity, at least unfortunately in the minds of many of our leaders. And this is so sad because what we wanted by this was to get everyone the access to the knowledge, not the information. Information can be traded, information can be sold, information can be made up. Knowledge has a real value, an intellectual value, and we shouldn't forget that. So unfortunately, even we occasionally take a few shortcuts in that value, and we'll occasionally say, oh, it comes from a good university, that research must be good. Or it was published in a very good journal, that must be good. Unfortunately, there have been quite a few high-profile cases recently which shows that this isn't always the case. But the reason we get away with that sort of judging the book by the cover is that most often it's right because there's a process behind each of these. There's a process behind the selections for universities. There's a process behind the selection before getting into a top journal. So it's the process that guarantees that there's some value behind it. And back to the knowledge example, that's also the difference between information and knowledge. There was the scientific process that made sure that the knowledge had some value. So because that's key to my talk, I'm just going to spend a couple of slides on describing the scientific process to remind us its important features. It's a natural process. We learn it ourselves. We pick it up as children. It's the way we explore and understand the world. We do our own experiments in gravity. We discover a lot about the world instantly. We discover that potential energy rapidly turns into kinetic, and not all collisions are elastic, unfortunately. We learn a lot about emotions when we study our parents' reactions to our experiments. So we study a lot of the natural world through a natural process, and that's how we discover gravity for the first time. Those of us that maintain that curiosity for the world and go off into research learn a wider and more rich process, a process that basically iteratively and collectively corrects and perfects and produces knowledge. So if I just take the gravity example just to go through a little further, so what we discover as a child is basically what Aristotle described gravity, and it survived 19 centuries, I think. And it was only when, in the 16th century, when Galileo did his experiment of dropping 2 unequal mass balls off the side of the Leaning Tower of Pisa, that things took a step forwards. In fact, as an aside on scientific precedence, did you know that that wasn't the first experiment? That in fact, 3 years prior to that, 2 guys in Delft University, in the church, the new church, did the same experiment. But Galileo got famous for it. Anyway, end of scientific precedence aside. It's such a strange and unusual thing that we repeat this again and again and again, generation after generation, just to make sure it really is true in all circumstances. Even the Apollo 15 crew repeated it with a hammer and a feather on the moon. And there's a video of that was actually streamed live to the world, again, to tell them this really is true. So with that level of knowledge of gravity, you can already make all sorts of wonderful machines, timepieces and things like that, but that wasn't the end of the story. About 20 years later, Tycho Brahe did some fantastic measurements of the planets and made some fantastic tables, incredibly detailed, the Rudolphine tables, and he tried to fit ovoids to that data, thinking of a geo-heliocentric model, and he just couldn't do it. After his death, Johannes Kepler, with exactly the same data, fitted ellipses and found his universal planetary motion. He got something to fit. So basically with the same data, different mindset, got some universal laws. That, together with Newton's descriptions, basically gave us our understanding that allows us to do all sorts of ballistics and trajectories, put up satellites and things like that. But again, that wasn't the end of the story. When Einstein started trying to think of how to marry his gravity with his special relativity, he realized that the only real way to do it was to assume that massive objects actually bend the space-time around them. This leads to some very interesting concepts that if you got a massive enough object, it must stop a light getting out of it, so black holes must exist. This was almost 100 years later. This was fantastically proved correct when the LIGO experiment measured the ripples of space-time from the colliding black holes that from a galaxy far away happened, and we measured them on Earth. So with this level of understanding of gravity, we can use in everyday devices like GPSs, which wouldn't work without that level of understanding. So basically, we've iteratively got to where we are now, and we're happy with our understanding, but perhaps we'll go further. One thing that seemed to take us a little bit further a couple of years ago was when a beam of neutrinos was shot through the Earth's crust, 600 kilometers, to an experiment in Italy. And they discovered that they arrived there too quickly, faster than the speed of light. This is fantastic. This opened up all sorts of imaginations of time travel and warp drives and everything. The applications were flowing. But unfortunately, they stood up in front of the audience at CERN, 500 physicists, and said, OK, we've done this, but we're not sure it's right. Can't quite believe it. And for hours, they were questioned, have you tried this? Have you tried that? Have you tried that? Finally, a couple of weeks later, they found out what the problem was, and unfortunately, the experiment wasn't done correctly, and unfortunately, we had to cancel the warp drives and everything. But they were brave enough to present what they found and discuss it with the community. So basically, this is our science. You measure things that you don't understand to make sure that you can have a physical understanding of them. You share things because you're not necessarily the best person to interpret them. You validate things because not everything that's measured is necessarily correct. And you replicate things just to make sure they apply in all sorts of different situations. And finally, you keep things forever, preferably, because it's not immediately that their impact will be understood, nor the possibility for them to be measured. So this is our scientific process. Fantastic. What's wrong with applying that in today's world? Well, today's world is a data-driven world, and therein lies the problem. If you look back just over 100 years when Marie Curie did her first experiments on radioactivity, she was able to describe her experiment in just a couple of paragraphs. The world at the time didn't believe her. They didn't believe her because she was young, unknown, and a woman, unfortunately. And so all the men read what she'd done and checked and checked and checked, did it again, could replicate it, and found she was right. So finally had to give her the Nobel Prize, which is fantastic. Fast forward to 90 years, when I did my experiment, also on radioactivity of a sort, in studying the weak force, I, with another set of 200 people, built a 6,000-ton experiment with 100,000 readout channels. Describing that in a couple of sentences is more of a challenge, and getting anybody to replicate it or even check what we did is certainly a challenge. So therein lies the problem: how to apply the scientific principles to a data-driven world. This is what I call the research iceberg problem. So basically what we now do, we continue to write a few paragraphs to describe our work, but it's wholly insufficient. It basically is a narrative. It's a bit of advertising for what we really did. To understand it, you actually have to get at the algorithms, the statistical methods, the workflow in which the data and the simulations were compared. But to understand them, you also have to get at the reduced data set. But if you want to do anything to change and do a different modeling, you not only need that, but you also need access to the actual reconstructed data set. And if you wanted to change, and also the code that did the reconstruction and the calibration and everything else. But if you want to change anything, you need the raw data. And the problem here is as you go down this iceberg, things get bigger and bigger and bigger to the enormous size. So how do you share, how do you validate, how do you apply the scientific principles to something like that? Now the answer, skipping back a few slides, the answer to everything nowadays is a web app, web store, web something. It'll do it. Throw it out there. It'll all get solved. And it's true, if you type in some scientific term, you'll get no end of pieces of information, data tables, plots, some of them good, some of them bad, some of them made up. You also have got no end of services to help you share some stuff, some fantastic services for sharing code. And you also got no end of services that will actually offer to do something with your data. Not sure what they'll do with it or why they'll do it, but they'll offer to do all sorts of things with your data. But sharing is not the same as publishing, and that's not the same as preserving. Even the best websites, NASA, loses objects. I love the way they say their cosmic object has disappeared over the event horizon. So they lose things, and they admit it. In fact, link rot is a real problem because people have started to put links, URLs in scientific publications. And studies show that on average, depending on the different disciplines, but 50% have disappeared. In other words, you can't access them after a year. So this isn't a particularly good way to publish your scientific output. All of these sharing sites have a problem. Yes, you can share. Yes, you can collaborate. They're fantastic for that. But you can also, with a single click, delete the entire repository. You can seed it to somebody else. You can transfer it. You can collapse all of the history into no history, and you can't see the version that was used before. So yes, they're great, but if you want to go back to some point in time, you may not be able to find it either. And companies, yes, well, companies, they change the world. Blockbuster revolutionized the film industry. Napster revolutionized the music industry. And they were gone a couple of years later. Google Books was going to revolutionize the libraries, but I'm afraid it didn't. So basically, there are things there that can do good, but you can't rely on them for the scholarly publishing process. So how do we do this? So let me take the example of CERN, how we solve this problem. CERN, so I'm not sure if you all know about CERN. It is where the LEP collider was, and we ripped that out and built in the same tunnel the LHC collider, the Large Hadron Collider, 27 kilometers long, 100 meters underground. And on that collider we've built 4 massive experiments which are measuring the collisions of protons, proton on proton, at nearly the speed of light. It produces a phenomenal data rate, 40 million collisions per second, with 150 million sensors in each detector. That makes petabytes of data per second. We can't possibly record all of that, so we trigger only 100,000 events a second. We record, again, a fraction of that. Then we run the calibrations, the reconstruction. We have tens of millions of lines of code just in that data reduction chain to get to the recorded data. Then we distribute it around the world. 167 sites then help us in the analysis. So this is a monster undertaking, and we've so far recorded 320 petabytes, 320 million gigabytes of data. So although CERN is a paragon of openness, we shared the web free with the world. We lead open source, we lead open access and things like that. When we said open data, not everyone thought that was a great idea. They said, well, yes, but think of the complexity, think of the scale, the statistics, and think of everything in between. And they came up with all sorts of reasons why this is going to be tough. Who else has got the knowledge of the detector to do anything useful with that stuff? Who else understands the methods of reconstruction or the tools of simulation? We haven't made our documentation accessible to anyone, so no one will be able to read about this stuff. You haven't got the resources, tertiary storage, or the computing to actually analyze. And if you don't do that, and you don't understand the statistical methods, how are you ever going to reproduce what on earth we did at a rigor that was required? So basically, they were worried that people wouldn't think enough, people wouldn't put enough effort in, people wouldn't do it with enough rigor, and therefore they would be bombarded with questions of people trying to analyze the data and not understanding it, jumping to false conclusions, and then they would need to contend them, spend time contending, or even worse, obliging them to actually redo some analysis that someone else has done just to prove that it wasn't right. So there were worry after worry after worry from certain quarters, and our response was, well, let's just do it and see what happens. So we created the CERN Open Data Portal. It took quite a while to do, and we put all of our knowledge of data management with our knowledge of digital libraries, put them together, and created this portal where we already share over I think it's nearly 2 petabytes of data. Importantly, along with the data, we share tools where you can access and do some visualization of the data, but we also share the entire virtual machine with all of the software stack that we use ourselves, literally everything, from the visualization to the analysis code and everything. So literally, you can access our data with our tools and do what you like with it. That was great. That hit the headlines. You can now hunt for the Higgs boson on your sofa. It's true. It's got to be a good, a well-equipped sofa, but you can. But what would people really do with it? Well, in fact, a lot of people accessed it and started using it just for the visualization aspects, as education, as training on statistical analyses, on all sorts of other things, machine learning that we hadn't intended when we shared it. But they weren't really particle physics. So can you really do somebody else do particle physics? Well, it took a couple of years, but then the first peer-reviewed paper appeared, made by people that had never been at CERN and never been on the experiments at CERN. They just downloaded our data and our analyses and managed to do real physics. So it's possible, and a few have been published later, one just 2 weeks ago, come out again. So yes, you can do it. It takes a lot of effort, but you can do it. So it's worth doing, even at our scale, even with our complexity. Okay, but I have to admit that to do this, it took us some time. It took several computer scientists, together with several physicists and several information scientists, the best part of a year to reconstruct. Because we found that even though we thought we had our hands on absolutely everything from the analyses that happened 3, 4, 5 years ago, it turned out not to be the case. We couldn't quite reconstruct the entire chain of analysis steps. We couldn't quite find all of the programs that had been involved. And then we had to describe them in a way that somebody else could actually understand what they were. So it took a huge amount of effort doing it after the fact. And this taught us that, in fact, the best way to do this is not to do it after the fact, to do it all the way along, is to change the processes to be up to date with open science practices. But that means changing everyone's habits. And how do you change everyone's habits just for an end goal like this? And then the answer is you you actually change it so it's helpful for them. Find something that actually makes a difference to the day-to-day life. So we basically said, what if we could give you tools that would avoid that when you got a new student, that they would take another 6 months to get up to speed, to find out what the last student did, which programs they ran, what order. In fact, find some of the programs because they aren't available. Or what if you heard somebody describing a technique at a conference and you were able to use exactly their code instantly, rather than having to go back and work out the algorithm and do it all yourself again, like at the moment? What if you wanted to substantiate some result to some internal reviewers, and it actually based on code you wrote 2 years ago that you actually hadn't saved? So all of these what-ifs meant that we could find things that would actually make a difference if we could make tools that would accompany people along the way. And as a result, at the end of the process, you would have all the tools, techniques, and data ready for when they were going to do the publication. They would all just be able to push a button and there it was. So that's what we've been working on, and it's called the Analysis Preservation Portal. So it's not a portal facing out to the world, it's a portal facing inwards to try and help the average researcher. And it basically accompanies them through the research life cycle. You can fill in the basic information about your analysis right off the go. When you start to code, we encourage to put into sharing repositories rather than local repositories, such that then you can put pointers to the code. The Docker images, the subsidiary databases and things like that. You can describe the data sets that were used. And all of these are actually active connectors, such that if they want to at any given point, they can push a button, and we've made a connector that goes and pulls back in and snapshots what they've been doing. So along the way, they can just gather things, collect them, and make sure that they're safe. Or right at the end, you can push the definitive button and archive the entire analysis as it was when finished. One of the most important steps is actually to get them to describe all the steps in the analysis chain in an understandable way, which is actually called the common workflow language. There are other ways to do it as well, that actually shows which are the steps of your analysis, what was the input, what was the output, what's the next step, and all the relationships. So this is a fantastically important exercise to do, and essential for then understanding all of the stuff that you've captured. Now, once you captured it, why not think a little bit further forwards? Well, if you captured it, why not be able to say, I want to do something with the data that they did, and with the analysis code that they told me about, and the computing environment, and that workflow. Couldn't I just instantiate it again? Run it on some cloud resource that I choose, not them, and then make the whole thing run and then return to me the result? That would really be reusability. So we did that. It's called the Reproducible Research Analysis Platform, RIANA, and demonstrated that you can. So not only have you got a utility from the classic way of doing things, but you also give them a new way of doing things, and other people new ways of accessing the same code. So we've started, this is just in beta, but we've started to put examples in now of real papers that were published and show that we can actually regenerate with a push of a button the actual analyses. And these are not simple analyses. This one here, the search for signals of physics beyond the standard model, has over 1,000 analysis steps, all described in that workflow language. Those are dispatched on this by this job execution controller, brings back the results, combines them, and presents it. And yes, you really can get to the result that was published in the paper. So it's beyond the concept, and it's an attractive way we could imagine offering to researchers something that would really take them into the future of open science. So this is all good. This is all the elements that we need, but we still have to get them into the publishing chain. So, publishing scholarship. What does that actually mean to get into the chain? Well, publishing scholarship has basically 4 different qualities. When you publish, you basically you get attribution. You get stamp. It was my idea. You get the validation of the peers looking at it. It's disseminated and it's kept forever. But the way we've been doing this for the last 300 years is basically, as I said, article-centric. And all of the tools that go around it are article-centric. But what I've just described of the new data-driven era is what you need is something research-centric. You need something that actually isn't reviewing a piece of text, but is reviewing the workflow. Was that a sensible way of doing the simulation and the comparison? That's actually reviewing the code. Is that a well-written piece of code that actually achieves what you state that it was meant to achieve? Was it the right statistical method that was employed or coded? And the data, was the data actually collected in a way that's believable? You can tell a lot by looking at the data and how it's structured as to whether that's true. But these processes don't exist, and we have many big industries that are working in this mindset. So how do we move them into that mindset? How do we get this transition into the data-driven era of a scientific process fit for purpose? So let's take a step back and look at something else that was a big phase transition that might be able to teach us something. The open source era. So the open source era that we live in now didn't always exist. In fact, it was around, well, when computers first were made, the code was a very small part. The hardware was doing all of the work. And it was only about the 1970s where this threshold was crossed and the software, the production costs of software outpaced the hardware. And there was a decision that software could be copyrightable. And from that moment onwards, closed source dominated, corporations dominated, everything was locked down, you couldn't make any changes, you couldn't put your innovation in, and you had to do exactly as they had said. At the same time, there was this ideal, this social movement that was started that said, this isn't right, this is my hardware, I bought it, surely I can do something better with it, surely I can make it run more efficiently. And so there were these two opposing ideals, if you like, the money-making generation that was providing useful services but unwilling to change, and those that wanted a better world where everyone could contribute to it. And it was only basically unblocked when some really visionary people, I think it was Tim O'Reilly, one of the finders of the O'Reilly books, that basically said, don't talk about free software, talk about open source as a development methodology. So not an ideology, but a useful methodology. And suddenly, the industries saw that there was a business opportunity. You could add value-added services on top of open source that somebody else had created. And you could do things like the training, the integration, the certification. And so they looked more positively on it, and I think there was a few things like Netscape putting out their browser as open source that suddenly started a cascade. New industries were created, and some of the old giants changed philosophy. So basically this moment when it became not an ideal, but actually something useful and could be used by the users and by the producers, created what we now live in the FOSS era. Some of the key attributes of FOSS are not just the sharing. Of course, you have to share the code, but you share it in a way that you can do collaborative development on it. Because the real gain from this old philosophy is that diverse minds create better solutions. And the other thing is that here it was closed and you didn't know anything about the processes that assured the quality, whereas here you could put processes on top that assured the quality. And you could track those contributions as well. So basically, now that we've got some of the giants moving in this direction, do we have a solution for open science? Well, I would say there's another thing to bear in mind, that basically all's fair in the commodity market. So yes, we have some giants. Yes, they love open source, but they run services that basically want to lock you in. They encourage competition, rankings and things like that. They encourage you to do the work, not themselves. And their entire game is to get you to engage. They're engagement platforms. That's why lots of things are free. Lots of things are really attractive just to get you on board, because their revenue is ad revenue. That's why everything's for free. So basically, all of the things that I list here are not the qualities we want in open science. So we have to be careful. And one of the biggest things I'd like to point out is that they're based on SLAs. SLAs are a trap for us in science, because the SLA basically says, yes, I absolutely guarantee this uptime. I absolutely guarantee that I won't lose it. I absolutely guarantee. But if I don't, I'll pay you out the economic value of your business or your data or whatever. Those buts make sense in business. Those buts don't make sense in science. What's the economic value of that data I just recorded? It's 0, so they'll give you 0 if they don't provide you the service. And this is a really important thing. We talk about intellectual value, not economic value, and that's not what the SLAs are written on. The other thing is they keep on giving away things for free, which is really exciting, and you all jump on top of it. But headline year after year is the cloud storage party is over. Amazon Drive cancelled their unlimited. OneDrive cancelled their unlimited. Just 2 weeks ago, Nirvanix, which is an enterprise-grade cloud storage server, went offline. They sent an email to all customers saying, in 2 weeks' time, we're going away. Take your data out before then. So that's the way that the industry runs. I would claim this isn't the best for us in science. There's actually a nice site called Killed by Google. It's an open source site if you're interested in going to it. There's 147 products listed there that Google made, attracted people to use, and then killed. 147. So, if it's not those, the commodity players, perhaps it's our classic publishers we should be looking to. And here I just ask you a question. The open source example I gave of the people that had vested interests in a certain business model and were making a huge amounts of profits and didn't want to move to a new ideology, does that ring any bells? Perhaps they could be our partners, but they have to go through that phase change that the software vendors did in the past into the new model before they can be useful to us. So that was the who. The how, the learning part of the how of open source was that it's not just the sharing that matters. So for open science, we have to get the open collaboration. The how is the open collaboration is the most important thing. So it's not sufficient just to share something as a black box. It actually has to be usable. So there's loads and loads of examples. I just took one of my favorite, which is a piece of code which is freely available. It's the famous fast inverse square root code. I don't know if any of you know this. It's a fantastic bit of code that it takes a floating point number, it squashes it into an integer, subtracts it from a magic number, reinverts it, subtracts it from 3/2 and gives it you back as an inverse square root. It's absolutely brilliant, but nobody who understands it. And is completely impenetrable, completely unusable anywhere else. So this is an example of exactly what you shouldn't do in open science. Your methods should be clear and understandable. They shouldn't use the last trick to be able to do things faster and better if nobody else can actually validate it or use it. This actually is a really clever trick, because when you stuff a floating point number into an integer, you're actually doing an approximation to a logarithm. And then when you right shift it, you divide it by half, and the magic number is, I think it's 2 to the power 127 square rooted. You subtract from that, and that does an inverse for you. It's absolutely brilliant, but nobody understands it, even though there are fantastic comments. So, evil floating point bit level hacking. So I mean, that really helps you understand it. And I'm not reading out the next one. So, open collaboration means not impenetrable methods, impenetrable code. It also means not entangled messes where if you pull one part of the spaghetti ball, everything else unravels or falls apart. So it really is building your scientific method, building your code in a way that's modular, there's clean interfaces, can be used in other circumstances. So this is rethinking the way you do things from the start. It's happening. This is great. The GitHub revolution is not just in the IT department, it's also in the physics department at CERN, and everyone is now using this as a collaborative sharing platform. There are communities building up, scientific communities, sharing best practice methods that they can be reused or optimized from their community and used in other different sciences. So this is happening, it's fantastic. So the open collaboration is starting. Again, we have to get these elements into the publication, the scholarship publishing business. So how we do that? So one way we hoped to help that at CERN was by creating something within the Open Air project. So Open Air was 30 different institutes across Europe getting together to help the European Commission help their open access and open data pilots. And what we did was we created something called Zenodo. We created it in the corner of the CERN data center, so on just one of our servers. There's 100,000 there. But it used exactly the same infrastructure, the same software that I just showed for CERN Open Data, and we just put it in the corner and then offered it to other people. So this is basically an open research as a service offering to the world. The idea being that you can capture any of the research outputs that are now needed in the data-driven era, put them in somewhere safe, get a digital object identifier for them so that you can use them in publications. This promotes all of these different objects into real, equal research objects for the modern era, the data-driven era. We then added certain facilities that make it more attractive, such as the versioning. This is really important for science. So if you put in a piece of software here and you say that's the paper, use that version of software, like I described the problems before, they no longer occur because you can say that that was exactly the one used for this paper and it is always available. If, on the other hand, you wanted to publicize something in a different way and say, for my latest version, get it like this, then you can go to the version and get the latest version. So you can either point to the whole collection or a specific version. So again, precision that's required for science. And you also get the usual things like statistics and things to encourage people to use it more. So back to the observation that sharing is not the same as publishing and preserving. So what does this do for software? Well, we teamed up with the GitHub team. We joined our APIs together such that when you do a tag a release, there's a handshake between the APIs, and then you can get a zipped file stuffed down into Zenodo, get a DOI issued and put back up onto the GitHub repository. This means that you can now snapshot something out of your collaborative platform and make it a publishable object. In fact, 75% of the world's software DOIs now go via this handshake. So it's quite a popular way of doing things. So this is now an enabler for traditional scholarship. So it helps when the big publications realize that they absolutely have to capture the data and the software as well, or the methods. There's somewhere that they can offload that responsibility to. And there are many. Zenodo is just one example. But it enables this to become a step in the right direction. It enables other institutes, nations and whatever to create their own repositories when they realize an artifact repository for science is needed and they don't want to do it themselves. So here the Lucerne repository actually just uses a community in Zenodo. And it helps in other ways that it allows you to make these other objects, or even an article if you wanted to put it in there, a reviewable object, because you can put it in Zenodo as a restricted object, and then you can share the restricted access links to it so that reviewers can only access it. You can put embargoes on such that it can then be released when the paper is accepted. So it enables traditional scholarship. But more importantly, it opens up the complete field for people's imagination, for the researchers to experiment. And they certainly are. They're creating all sorts of things as this as a base and everything else on top. So there are overlay journals like this called the Journal of Brief Ideas. If you can express your idea in any way under 200 words, you can publish this as a brief idea. So this allows you to, if you've done something with your data, but you've got another idea to do something later, you can say what that idea is, get a DOI on that, even if you haven't got the chance of doing the analysis immediately. An interesting thought. Some people like it, some people absolutely don't like it. The point is that this enables new ideas in science like that. Another one, the Rescience Journal, which actually within GitHub is doing a peer review process and then pushing the lump down to get the DOI in Zenodo underneath. And this is a journal which absolutely encourages computational scientists to re-implement something that already exists in a better way. So this is basically improving algorithms, improving the science behind the computational science. Publishing of software, there are many different ways of doing it. This Journal of Open Source Software basically says, here's a quick one-pager that points to, and it describes where the actual code is, back down in Zenodo again. So it just enables things to be done differently. Zenodo is not the only one, but it's just a platform where you can experiment. There are other excellent things where I just highlight one here, protocols, which just allows the biological sciences to do to capture their methods and things like that. So this dissection of the science into all the different elements, the different atoms, is starting now, and hopefully will allow us to rebuild it in a new way, ready for the data-driven era. Another interesting one is a collection, another community in Zenodo, which is the biodiversity community, who have decided that the most important thing to them are the taxa. And to understand a taxa, you should see what it's actually describing. So they've gone across their entire literature, and they're extracting out of the literature the definitive picture, the definitive photo of the thing being pointed to by a taxa, and they're giving each one of those a DOI as a separate instance in Zenodo. So these now become the research objects that they're pointing to in all of their scientific journals. So again, just rethinking the way you do it, because in the past you'd have to say, go and look at that journal. You'd find the journal, you'd have to find the page, you'd have to find the picture. It's much more obvious. This is just, that taxa is describing this object. So the exciting thing is, by starting to put some building blocks there, people are doing all these different new ideas in how to do science in the data-driven era. This makes it much more possible to do it in a collaborative manner, and it also makes it possible for the expertise to be identified and to be distributed. So basically the computation is a step that can be isolated, it can be assisted, it can be shown as a result, it can be peer-reviewed on top of it by the experts in computation, and that can be separate from the data curation. And so this idea has come up of badging exactly in a journal what your contribution was. So this is fantastic for those of us that, that are deep in the heart of it and didn't actually get the recognition for those activities before. It also means that the boss that keeps on putting his name on everything now has just got his name under, he got the funding, which is really useful, but he wasn't the one you go and ask to understand the computation. Go and ask the person that's listed as responsible for that. So this dissecting of the research process, distributing it into more modern tools, and then re-aggregating, I think really could be our answer to a future world of data-driven science. So in conclusion, market or commons? Well, there are goods and there are services. I hope I've convinced you that knowledge is absolutely not a resource that should be governed by the state or the market. It's something that should be self-governed by those of us that create it. And that's the definition of the commons. So for me, that's absolutely clear. But on the other hand, the scientific process, which is so key to all of our research, that needs new data age services. There is a huge potential for the market to add those services that would really accelerate our science. But quite a few of the actors that are currently there really need a phase change, like in the open source era, before they're actually ready and to give the researcher the driving seats to determine what those services should be. But if that could happen, we really would have open science that could flourish in this collective, corrective, and distributed manner that we dream of in the future. Thanks.
Thank you very much, Tim, for this very inspiring talk, I think, and for showing us the good reasons to go open. We will open the floor for questions. We will try something I've never seen before, but we have a microphone that you can throw, so wait for it before you ask your question. I'm sure you have a lot of questions, so what are your questions for Tim? Don't be afraid of the microphone. Marta will not hit you in the head with it. Jasmine.
First of all, thank you very much for the really inspiring talk. It was really, really nice. It's actually a rather simple question. So we, as a data stewards, really like this functionality with the GitHub integration with Zenoda, and we are telling researchers to make use of it. Mm-hmm. And we were wondering as a team whether it will be possible for GitLab as well.
So in fact, we'd love that to happen. There are a few tickets open on GitLab as well, where people have asked GitLab themselves to help. And people had open tickets with us as well. For the moment, it's just a question of effort, and we haven't actually got it around to it. But yes, it's on our wish list. We'd love to do it. In fact, at CERN, we run our own instance of GitLab, so we are motivated to do it at some point. But it needs a handshake, so it needs them to actually help us as well.
Alistair? Catch it? Oh.
Do you believe that what you talk about is true for all disciplines? In that many disciplines think they have a different approach to data and sharing of what they do, and how much is what you've done and your vision influenced by the type of methodologies you have at CERN?
Absolutely. We have a very open stance on everything. From our convention onwards, we've always been open. We're obliged to share the findings. So yes, it's in our blood to do it like that. But as I say, that didn't mean that this next transition that we're going through was universally accepted and obvious. And I think those reticences are evident in other sciences even more that perhaps don't have the same openness. So I think there are problems that can be overcome just by showing that it's possible. But it's true, there are some other sciences that simply have different types of problems, and this won't answer their problems. It will answer some of them. For instance, the medical field. There are some reasons why you would absolutely at the moment believe that the only way of doing it is to keep it locally, keep it in the hospital, keep it somewhere at the researchers, and a central solution may not be appropriate. So no, I don't believe that we answer every discipline, but I think that by showing that at least some of the complex problems are easy to overcome, you can convince more people to try. And then what I was talking about, the value-add services, will be created by other people that think of these extra bits that are needed for the other sciences.
Yes. Victor.
Thanks for a nice talk. I really enjoyed the metaphor with the open source software.
Thanks.
So now your main aim is to open it up for scientists. But could you, if we extrapolate a bit, could you do it for the public at large? Because if I get a Google Cloud, I get $300 worth of compute power. I can get it for 150 euros. I can buy a small genomics tool that gets me genomes. I mean, what's stopping anyone from doing this? And are you somehow providing the general public, who's pretty much paid for this, with the tools to reproduce it?
So, if I understand rightly, there's several aspects to what you're asking, because what Google can give you in the compute cloud is not what we're offering here. In the data storage, there are many vendors that could offer pure data storage, but to add the services on top, such as the DOI, which is a guarantee of access to that data, or a commitment to move it somewhere else if you can't serve it anymore. Those are not services that the commodity market can give you. Also, the commodity market is really clever. They might give you unlimited storage, but then they charge you to access it. So, okay. But what I was trying to say is the style of their services doesn't match science one for one, and you've got to be very careful. If you're saying whether or not the open source stack that we have could be reinstantiated by someone else, that's another question. Yes, of course it can.
Or maybe to rephrase my question, so now you seem to target science and researchers in general.
Mm-hmm.
Could you also target the general public, the world population? Can someone who's born in China in 10 years, who has no scientific education whatsoever, use it? Would you like them to?
So what we ask is that people store research objects in it. And we have in our terms and conditions that you, if it's not a research object, then we'll give it back to you, delete it. So it's not for any old stuff. CERN ourselves cannot guarantee an infrastructure for the world for free, of course not. But anybody can use it. There's no restriction. So somebody that's done an experiment in their garden, measured the water, the rainfall, yes, they can put their data there. That's research. That's valid to be shared with the world. So it's not on who you are, it's what you're doing. We don't want to help the gaming industry, help all sorts of other things. We want to help research.
All right. Here there is another question. Marta? Thank you.
Thanks. Based on your experience at CERN, what would your advice be towards, well, a university like Delft University? What is the most important steps at this point in the transition, so to speak? The most important decisions to make to advance open science in a university environment?
So I think the example of the CERN Open Data Portal shows us that obligation only gets you a certain distance along this path. Making useful tools that assist the researchers to do research better, faster, easier, more collaboratively, that makes a difference. So the electronic lab notebooks, the things that they're going to use every single day and become more efficient at, and as a byproduct, capture more of the elements that you need to do open science. I think that's an approach that really will make a change, because then people want to do it, not obliged to do it. But finding those things, the key change, is more hard.
More, yeah. Nice.
Thanks once again for the presentation.
You're welcome.
I'm wondering how much, so I'm working in a field where a typical experiment is very small.
Mm-hmm.
The big data is maybe a couple of gigabytes, well, not more. And a typical team size is maybe also a couple of people. And I'm wondering how many of your lessons could be translated to the different workflow, because, for example, I was looking at the CERN analysis preservation tool, and while I see that it definitely allows to reach a very high degree of reproducibility, it also seems to be much more labor intense. So I'm wondering how to incorporate a similar degree of reproducibility and also transparency that machine readable formats enable into a much more flexible workflow and a smaller scale one.
So as I say, I just described a bit like your question, my worldview, because I've been helping my science. But it's clear that other sciences are exploring in different dimensions. And one of them that is especially popular at the moment is notebooks, computational notebooks. So they can describe in a very visual way a small set of steps, and they can link exactly like I described to the actual computational engines behind as well. So perhaps on a smaller scale a different approach will be more useful, I don't know. But if you saw in my diagram, in fact, one of the things we've done in the Rihanna was actually put in some computational notebooks as well. So to show that no matter how you describe it, how simple or complex, the same machinery could instantiate it again. So I don't think it needs to be complex to use this. You could just put a fully described one item in there and just get it so that it's preserved and reinstantiatable, and that would probably be enough. But I don't claim that I could instantly translate my complex workflow into a simple one.
Just to clarify, the computational notebooks, you mean the Jupyter notebooks?
For instance, yeah.
Right.
Yeah.
More questions? I see Alistair very... Okay, okay. Somebody else? What about your data on the open data portal?
Mm-hmm.
Are they also in Zenodo available with the DOI, which is...
So the open data portal is issuing the DOIs for the CERN data. Yeah. And the stack that we have behind it is essentially the software is open source software. It's called Invenio. It's the digital library software that we married with the data management. That stack is underneath Zenodo. So Zenodo was just our way of sharing exactly the same functionality with the world. But the question is why we shared a different stack. Well, if you interact with the CERN Open Data Portal, you find that it's extremely customized to help you to delve into the data interactively. So there are interfaces where you can interact with the data. There are descriptions of the data. There is metadata described for our data specifically. So it was a very specific example, which we then generalized into Zenodo. So yes, we perhaps could do it the other way around, but we started, we did something for ourselves and we generalized it for everyone else. And we like the functionality that we've got, the interactivity, the specificity. Now, if we could build that on top of Zenodo for every different science, that would be great. Yeah. But that would take a huge amount of effort.
Yeah.
So Zenodo is a simpler interface, more generic and more general than our CERN open data portal.
So if you speak to many researchers and often senior management here at Delft, one of the big fears, which you sort of addressed but didn't head-on addressed, is I've created all this data in my infrastructure here. If I publish it, I'm going to be scooped. And somebody else will come up with other ideas. And this is my data. This is my work for the next 3 or 4 years.
Yeah.
How do you deal with that?
So this is very science specific and it's very data set specific, and I don't have a universal answer. So what I showed in the CERN Open Data Portal wasn't made open the day we took it. It was actually made open 5 years after we took it. In those 5 years, we published on average 200 papers a year, something like. So there's 1,000 papers gone out. We think that by that stage, we've seen most of the important things, and we're not going to get much scooped. But there's value from other people doing things. So I think there's this decay function in each science, in each field, that says how much you can produce from your knowledge quickly and how much you'll never get to but someone else could get to. And that when you cross that threshold, you should put it out there. I'm not a believer in instantly putting it out, and I'm certainly not a believer in never putting it out. But somewhere in the middle there is science by science.
Okay.
So what is your opinion about open lab notebooks, for example, which is also some part of open science where people are posting daily experiments and...
It's all great. It's as I say, it's subject specific, and if that works for them, that's fantastic. I, as a researcher in my previous life, liked to experiment a little bit more first, and then the thing that actually seemed to work, I would prefer to then share that with my peers, rather than all the silly things that I tried that were absolutely stupid and were not going to work. But other people work differently, and again, it's what you're comfortable with.
Okay, good. More questions? No? Thank you very much again, team, for coming here. And I would like to use your computer to show that this is actually the first presentation of a series of presentations in an event that we call the Future Forward Science in the Open Era. So there will be more events during the year. In the postcard you can see the next one, that is designing open hardware for 21st century science. That will be on the 10th of April. So reserve today. Also invite your colleagues to join. We hope to have very interesting discussions like the one today. And I would like to invite you to stay a little bit for a small catering, small cocktail, and enjoy the presence of Tim and ask him all the questions you couldn't ask now in the session. Thank you for coming. Thank you.